Hi, my name is Tom Hoeffel, and this channel is all about helping students learn chemistry. In this video, we're going to try to compare and contrast sigma and pi bonding. But before we get into that, we need to talk about what a covalent bond is. Basically, a covalent bond is when we have two electron orbitals that overlap each other. Okay, and since they're overlapping each other, they can share their electrons. This is different than an ionic bond, which transfers electrons. So once again, a covalent bond is when electron orbitals overlap so that they can share their electrons. Now, in this video, we're trying to discuss the difference between a sigma bond versus a pi bond. So let's go to talk about the sigma bond first, and then we'll try to compare that to a pi bond. A sigma bond is something that occurs on the internuclear axis, okay? And I have a line here of kind of like element A and element B, and if their electron orbitals end up overlapping, maybe something like this, right here is actually where the covalent bond exists, okay? Now, the internuclear axis is where you take the nucleus of one and the nucleus of the other, and if you just drew a dotted line through that, that's what would be the internuclear axis. So if we have two orbitals that come together, in this case, it's going to be like two spheres, okay? So it'd be coming in something like this, and they start to overlap, okay? That overlap is actually the covalent bond, and it's occurring on the internuclear axis. Now, what I have an example of here is an s orbital and an s orbital. So the two spheres, okay, that overlap on the internuclear axis. Well, I could also have p orbitals that overlap on the internuclear axis, okay? So I have these models here to try to show kind of like what a p orbital would look like. Remember, p orbital has two lobes, okay? So these little pieces, plastic pieces here are supposed to be like the p orbitals. And if they come together, they could overlap, okay? And that overlap is actually the covalent bond. And that would be occurring on the internuclear axis. So the first bond is always on the internuclear axis, okay? And since it's on the internuclear axis, we call that a sigma bond. Now we could also do that with a sphere. Like if this is a sphere, okay, and this is a p orbital, they could overlap. They could be small spheres or they could be larger spheres. As long as you have electron orbital overlap, you have a covalent bond. Now there's this other overlap that we could talk about as well, which are hybrid orbitals, okay? And I want to remind you that a hybrid orbital, whether it's sp, sp2, or sp3, is typically some tiny lobe that's insignificant, followed by a big lobe. So this is an expression for an sp orbital, an sp2 hybrid or an sp3 hybrid orbital, okay? And if they overlap with any of my spheres or any of my, dumbbells or two lobes in a node with the orbital, okay? As long as you have electron orbital overlap, you could have a covalent bond. So I could have sp overlap with a sphere, sp overlap with a dumbbell, or sp overlap with another sp orbital. And then the same thing would be true for sp2 or sp3. So all of those bonds are going to occur on the internuclear axis. So let's talk about some examples of what that would kind of look like. And I got lots of pictures here that I'm going to display underneath the document camera, okay? So if we had hydrogen and hydrogen, or hydrogen and chlorine, or chlorine and chlorine, that would be some of the examples that I just explained. So let's go into the hydrogen-hydrogen bond first, okay? So if we had hydrogen and hydrogen, okay, we would have two spheres, and if they overlap, the covalent bond would be taking place right here, okay? If I have HCl, okay, it would be a sphere with what I call a dumbbell. Some people call it two lobes in a node, but the dumbbell is kind of like what I call it in class. So if I have this dumbbell that overlaps with the sphere, right here is this covalent bond. Of course, you could have two dumbbells come together and overlap, okay? And the covalent bond for chlorine versus chlorine would be right here. So this is an example of S and S, S and P, and then P and P, okay? Well, what about those hybrid orbitals? What kind of electron orbital overlap would they do? Okay, so this next one is CH4, okay? Now, what kind of orbitals are overlapping for the carbon, okay? And from our last lesson, we learned about hybridization, specifically of carbon. And to do hybridization, you have to count the number of electron domains. There's 1, 2, 3, 4 electron domains around the carbon. So if there are 4 electron domains, carbon is going to go through sp3 hybridization. I have an example from a previous problem that I've done in class, but basically this is carbon's electron configuration. We promote the electron, and then if it's sp3, we grab all of these and we get these 4 equal orbitals, all with an electron that can overlap with an orbital of hydrogen. So a hydrogen atom's gonna come in here, or electron, and another hydrogen's electron's gonna come in here, and another hydrogen's electron's gonna come in here, and finally a 4th hydrogen electron will come in here for a total of 4 hydrogens to form all of these covalent bonds. Now, if you forget how to do hybridization, I do have a video on that. So if you are a little bit lost on the hybridization piece of this lesson, I do recommend going back and watching the video on hybridization, okay? But if carbon never did any hybridization, if it just stayed in its ground state, you can see it could only make 2 bonds, one right here and one right here. And carbon's making 4 bonds in CH4, 1, 2, 3, 4. So this is kind of like why the hybridization has to take place. In addition, these p orbitals are locked in at 90 degrees, okay? So this is like the X, Y, and Z axis, kind of like if we had p orbitals kind of like on the X axis and on the Y axis and then the Z axis, we would get something that looks like this. And all of these, if hydrogens came in to bond here, they would be at 90 degrees, okay? Well, when you do the hybridization, it actually unlocks the angles, okay? And if we have 4 equal kind of like orbitals, they will spread out as much as they possibly can and kind of form this tetrahedral shape, okay? That is really symmetrical. And that's what I kind of try to draw right here, okay? So the type of orbital that carbon is giving out right here is a hybrid orbital, and it's called sp3, and there's 4 of them. So remember, our hybrid orbital is an insignificant lobe, okay, followed by a significant lobe. That's what a hybrid orbital looks like. So if we had kind of like an insignificant lobe and then a big lobe, okay, and that takes place in all of these directions, this is kind of like what we would get right here, something that would look like hybrid orbitals. Now, the hydrogens are gonna be spherical, and right here would be 1 covalent bond, another sphere would be another covalent bond, and another sphere here would be another covalent bond, all the way around so that there's 4 covalent bonds. Now, I have a better picture of this from my textbook, so let's take a look at that. So when there's sp3 hybridization, it's 1 sphere and all the dumbbells that are on the X, Y, and Z axis, and they kind of change, okay? So it's no longer spheres or no longer dumbbells. We get these hybrid orbitals, and they get in all these different places because they're trying to spread away from each other because of valence shell electron pair repulsion theory. And it ends up making this tetrahedral shape. So the electron orbitals of the carbon are gonna be these 4 sp3 hybridization, and then these spheres of hydrogen kind of come in here and do their overlap at each of the orbitals. So in the molecule CH4, we have an overlap from the carbon is gonna be sp3 3 hybrid orbitals overlapping the s orbital of the hydrogen, okay? Well, let's take a look at BF3. Well, BF3 is gonna have hybrid orbitals as well, but instead of having 4 hybrid orbitals, okay, there's going to be just 3 of them. And if there's just 3 of them, okay, we're gonna call that sp2 hybrid orbitals. And I have a better picture of what sp2 hybrid orbitals would look like, okay? So if you took 1 s orbital and 2 p orbitals, they're going to blend together to once again form these hybrid orbitals, but they're gonna get 120 degrees away from each other to form this trigonal plane shape, okay? Maybe something that would look like this molecule right here. So when we take a look at the type of orbitals that are overlapping, it's gonna be the sp2 hybrid orbitals, and it could be a p orbital from the fluorine, okay? Just when we do hybridization, we typically only talk about the central atom. So we're just gonna say that it's a p orbital from the fluorine, just like the p orbitals of chlorine overlapped each other. We're gonna say the p orbital of fluorine is overlapping the sp2 hybrid orbital of the boron, okay? Now, when we get into multiple bonds, things change up a little bit, okay? So let's kind of go back to our first page of notes and talk about pi bonding, okay? So when we have pi bonding occurs perpendicular to the internuclear axis. So if we were taking a look at just p orbitals, okay, if they're on the internuclear axis, they overlap like this, kind of like if this was the x-axis, okay? But if they keep getting closer to each other, the p orbitals that are on the y-axis or the z-axis, if they get close enough, there's gonna be overlap there as well. And this is the pi bonds, okay? So if they overlap, this part overlapping and this part overlapping is actually what we call a pi bond. And I have a picture from our textbook that kind of show the difference of something that occurs on the internuclear axis, which is a sigma bond, versus a pi bond. Okay, so this is a nice picture of these p orbitals getting close to each other, and everything's occurring on the internuclear axis, so this is going to be a sigma bond, okay? But if these p orbitals, okay, are on the y-axis or the z-axis, as they get close to each other, we start to get some smearing or some overlapping that is perpendicular. It's not occurring on the internuclear axis, okay? It's occurring perpendicular to the internuclear axis. And we call those pi bonds. Now, pi bonds will always be the second, third, or whatever extra bond that you might have, okay, beyond the initial sigma bond, okay? So when we take a look at carbon dioxide, we want to take a look at what type of orbital is the central atom overlapping, okay? And we gotta count our domains. There's 2 domains, so that means it's going to be an sp hybrid orbital, okay? Well, let's take a look at what sp hybrid, the hybridization of carbon looks like when it's sp, okay? So when it's sp, okay, it's just gonna grab 1 s and 1 p, and these 2 electrons, like kind of like right here and right here, are gonna be what occurs on the internuclear axis, okay? So when carbon and oxygen bond, okay, the first bond, okay, is gonna be a hybrid orbital that's gonna overlap with one of oxygen's orbitals, okay? So the first bond is gonna be an sp hybrid orbital of the carbon overlapping with a p orbital of the oxygen, okay? So we're gonna call that the sigma bond, okay? The first bond that occurs, and that's gonna occur on the internuclear axis, okay? Now, the second bond is gonna be a pi bond. So I'm gonna go ahead and let's see if we get this on the document camera so you can see. The second bond is gonna be the pi bond. So this is always gonna be the first bond, and then the second bond is gonna be the pi bond. Now, pi bonding electrons are always going to occur perpendicular to the internuclear axis, and they're going to involve p orbitals, okay? So if we take a look at the carbon, remember, it had more than just sp hybrid orbitals. The sp hybrid orbitals are the ones that are going to the left and to the right, okay? The one to the oxygen on the left and one to the oxygen on the right, okay? And it's going to form the sigma bonds. It's these electrons up here that are perpendicular to the internuclear axis that actually is going to be the pi bonds. So what's happening here with the oxygen is that you have p electrons from the carbon, okay, that are going to overlap with p electrons from the oxygen. And this is going to occur either on the y-axis, okay, or on the z-axis as they get close to each other. It's not going to occur on the internuclear axis because the first bond that occurred on the internuclear axis was sp hybrid orbitals with p orbitals of the oxygen. When we get to the pi bond, it's always going to be the p orbitals that are overlapping because it's actually the p orbitals that are perpendicular to the internuclear axis. And I don't know, hopefully all that kind of like makes sense there. We're kind of like getting pretty out there, but we're all talking about kind of like what orbitals are overlapping with each other. So once again, here is going to be S and S. This is going to be S and P. This is going to be P and P. Here's an example of an sp3 hybrid orbital. Remember, there's going to be 4 hybrid orbitals, okay, called sp3. This one has 3 orbitals, so we call it sp2. This one just has 2 hybrid orbitals, so we call it sp, okay? Let's talk about a couple more molecules, okay? One that I'd like to talk about is ethene, okay? So let's try to draw what an ethene would look like. Ethene has 2 carbons and 4 hydrogens. So right here, we're gonna take a look at this carbon and try to figure out what type of electron orbitals are overlapping with the carbon and what orbitals are overlapping with the hydrogen. So I kind of want to talk about the CC bond and the CH bond as far as what type of orbitals are overlapping, okay? Well, it all comes down to electron domains. This is going to have 3 electron domains, and if this carbon has 3 electron domains, then it's going to make sp2 hybridization. So the carbon, the first bond that comes in, it's always going to be sp2 hybrid orbitals. Now the hydrogen's pretty easy, that's just an S, okay? And for the carbon, remember there's going to be 2 orbitals. The first one, okay, is just going to be sp2 over sp2, and that's going to be our sigma bond, okay? Remember, that's the first bond that occurs on the internuclear axis. But since there's a second bond, remember, those are going to be p orbitals that are overlapping. And I have a nice picture that shows the orbitals of ethene, okay? So remember, ethene is going to be sp2 hybrid orbitals. So if we take a look at these sp2 hybrid orbitals, we got 1, 2, 3 sp2 hybridals. One's going to the carbon and the other 2 are going to the hydrogen. And that's true for the other carbon as well. 1 to the carbon and then the other 2 to the hydrogen, okay? So right here is the bond that occurs on the internuclear axis. It's going to be an sp2 hybrid orbital overlapping another sp2 hybrid orbital for the first bond, okay? Now the second bond, which is going to be what we call a pi bond, and that's the lesson today, is understanding the difference between sigma and pi, is going to occur perpendicular to the internuclear axis. So this is the carbon-carbon pi bond. It's occurring up here, okay? And then, so our first bond is sigma, and then the second bond is both of these, okay? So this is not 3 bonds. It's not 1, 2, 3. It's 1 and then 2 as the second bond, okay? And then when we add our hydrogens in, okay, we can see that it's going to be sp2 hybrid orbitals overlapping spheres of hydrogen, okay? And that's kind of like what I have written in my notes. It's going to be sp2 hybrid orbitals of carbon overlapping spheres, or s orbitals, of hydrogen, okay? And there's going to be 4 of them. There's overlap here, overlap here, overlap here, and overlap here. And those are all sigma bonds because they're the first bonds that occur. So remember, between 2 elements, the first bond that occurs is always a sigma bond, and it occurs on the internuclear axis. If there is a multiple bond, a second or third bond, that's always going to occur perpendicular. Okay, let's talk about one more, okay? Actually got a couple more, but one major molecule is gonna be ethine, okay? And this is what ethine looks like. There's a triple bond between the carbons, but I kind of want to do the same thing. What type of orbital, electron orbital overlap occurs between the carbons? And then what type of electron orbitals are overlapping for the carbon-hydrogen bond, okay? And it all comes back down to counting your electron domains. If I have 2 domains, then it's going to be sp hybrid orbitals from the carbon. Now, if it's going to the other carbon, it also is going to be sp for the sigma bond, okay? For the hydrogen, it's just going to be an s, okay? And that 2 is going to be a sigma bond because it's the first bond that occurs, okay? Now, the second and third bond in between the carbons is not going to be sps, okay? It's just going to be p orbitals for both the second and the third bond, and we are going to call those pi bonds. I got a picture of this. Let's take a look at it, okay? So once again, the first bonds that are occurring here, because of the 2 domains, so 1 domain, 2 domains, okay, we're going to have sp hybrid orbitals. So right here, as you can see, this is the sp hybrid orbitals of each of the carbons that are overlapping, and that's a sigma bond on the internuclear axis. The other 2 are going to be perpendicular, okay? So the first bond is going to be here, but the second bond is going to be like this, and then the third bond is going to be like this, okay? And the picture kind of shows that right here. So this could be kind of like the second bond, okay? And then the third bond would be kind of coming out at you and behind, okay? So right here's the sigma bond, here's the second bond, which is pi, and then here's the third bond, which is pi as well. And then when we throw in the hydrogens, it's going to be the sp hybrid orbital with the sphere orbital. So sp hybrid orbital with the sphere, and it happens on both sides. Okay, the last thing that we need to talk about is what delocalization versus localization means. We have that in our notes here at the very, very bottom. What does it mean if p orbitals are localized versus delocalized? Well, the examples that I want you to put in your notes here is that carbon dioxide is localized, and some examples of delocalized electrons that are pi are going to be like the nitrate ion or benzene. Now let's kind of go back and take a look at our carbon dioxide, okay? Remember, for our carbon dioxide, there's 2 domains, so it's going to be sp hybrid orbital versus a p orbital that are overlapping as the sigma bond, but then we also have pi bonding that occurs with the p orbitals. Now those p orbitals that are overlapping are specifically between this carbon and this oxygen. So that's why we say that they're localized, because it's definitely occurring just between these 2 atoms. Now on the other side, the pi bond, same thing. It's only occurring between this carbon and this oxygen. So we call those localized pi bonding electrons. So when do you have delocalized pi bonding electrons? Well, from our notes here, we know that's going to occur with the nitrate ion. Okay, so let's take a look at the nitrate ion and the benzene ion. Now, when you do the nitrate ion, you're gonna find out that it's in resonance, okay? And some people think that the double bond is in these different locations, but remember, resonance is a blend of all three of these pictures together. So it's actually 1 1/3 bond here, 1 1/3 bond here, and 1 1/3 bond here. Well, how would that look like as a picture, okay? Well, if I pick one of these resonance structures, just one of the three, okay, it looks like there's a double bond in one of them, okay? These lines would represent the sigma bonds, but it looks like the double bond would occur between only two of these, and it almost looks like it's localized, okay? But remember, there's three resonance structures. That pi bonding actually exists here a little bit, and it also occurs here a little bit. So when it goes through resonance, those electrons are not between just two elements, it's spread through the entire molecule, okay? And that's why we call them delocalized. So you have delocalized electrons when you have pi bonding and resonance. So if that's a fact, then we're gonna have resonance with our benzene as well. So let's take a look at what benzene looks like. I got a million pictures over here, so I gotta sort through it, okay? Got my benzene, okay? Benzene is a 6-ring carbon chain, okay? And it's gonna go through sp2 hybridization to make the 3 hybrid orbitals, okay? And everything that you see over here is gonna be the sigma bonds. These are the first bonds that are occurring, okay? So if this is going through sp2 hybridization to make those 3 purple orbitals that you see, okay? Well, it also tells us if you do sp2 hybridization that you got some p electrons, okay? And over here, okay, is all the other p orbitals, and they're gonna end up doing the second bond in benzene, okay? So if we looked at this, okay, before we look at the resonance, those pi bonding electrons, we could have double bonds in these locations or these locations, okay? But since there's resonance, it's both of these. So these electrons are not gonna be localized. When it goes through resonance, okay, we spread those molecules throughout the entire problem, okay, or the entire molecule. So once again, you have delocalized electrons when you have pi bonding, which is these double bonds, and resonance. So I hope all this information helped you understand, you know, the difference between sigma bonding and pi bonding. I know it's a little out there when we talk about electron orbital overlap, but I'm hoping to put some good pictures in your head of what that looks like. And I just want to remind you that delocalization only occurs when you have pi bonding, which is the second or third bonding, okay? And remember, you gotta have resonance as well, okay? So if there's resonance, okay, you're gonna have delocalized electrons. If there's only one model that works, then those pi bonding, the double or triple bonds, they're gonna stay localized just between two elements, okay? If any of this information has helped you, I encourage you to smash that like button, subscribe, leave a comment. When you leave those comments and when you like it, it really helps share this information with other students that want to learn chemistry in the easiest fashion as possible. And I know we're kind of out there, but I believe you know, this is presented in a way to help people understand in the easiest way possible. So I appreciate your time. I appreciate the like, subscribe, and comment. And please do that. Have a good one.